Section 9, Part C. So we've talked about the basics of the central limit theorem. Anytime you select a large number of individuals from a population of numbers, don't care what the shape is, with mean mu and standard deviation sigma, then the shape of the randomness of the sample mean, the shape of the randomness of the average of the numbers you get, is approximately normal shaped, centered in the same place as the population, but the standard deviation is the populations divided by the square root of n. And from there we saw how to do some examples. We had both roots here, right? We had that this was approximately true for large n regardless of what shape you had, but if you had the normal shape, then it was automatically true. I want to explore another example of that root. So we've talked about the basic idea of how to compare averages, sample averages, to numbers. What's the probability that the average of the numbers you picked is less than this, more than this, between these, using our normal chart procedures. Now I want to take an example of a more advanced problem. This harkens back to what we did in section 6 when we were comparing two variables. In that section, the example we did here was golf scores. So I want to do something similar here and look at the various problem types we can do. So I don't actually do the first problem type. I do the 2, 3, and 4 of 4. So example 3. This is a more advanced example of how to do these type of problems. So let's take a foray to Middle Earth. The heights of dwarves in general are approximately normally distributed, with mean 4.8 feet and standard deviation 0.5 feet. The heights of elves are normally distributed, with mean 6 feet and standard deviation 0.2 feet. So first of all, notice that elves on average tend to be taller than dwarves, which is to be expected, but also their heights tend to vary less than dwarves' heights vary. So there are 4 basic problem types you can do here. Type number 1 I didn't bother to do, which is our old section 3 stuff. You know, we can look at the probability that a random dwarf is less than this height, but more than this height, between these heights, or we could do the same kind of thing for an elf, just using our usual rules. What's the probability that a particular dwarf is, well, let's do it this way. What's the probability that a particular elf is less than 5.8 feet tall? Well, you know, you would subtract this, and then divide by this, get the z, look it up, and since it's less than, you're good to go. Just get it on the chart. Another problem type that we could do is the type of problem that we did in section 6 when we were comparing variables. Pick a dwarf, pick an elf, and of course we'll use random variable d for the dwarf we happen to pick, and random variable e for the elf we happen to pick, and talk about the probability that the random elf that we happen to pick is shorter than the random dwarf we happen to pick. That is, E is less than D. What the elf happens to be is less than the height that the elf happens to be is less than what the height the dwarf happens to be. Notice this is exactly the same as the problems we did in later section 6, which was comparing two variables. We can talk about one person's golf score or another person's golf score. We can compare the golf scores. What's the probability that Sam has a lower golf score than Jack? Or any of those examples that we did there. And we saw how to do them. You subtract to the other side so that we're comparing. You don't compare variables per se, you turn them into a new variable and compare them to a number. So we'll subtract d from both sides. Saying that e is less than d is the same as saying that e minus d is negative. I mean, you're subtracting the bigger one. E minus d is less than 0. So nothing particularly new here, it's just another example of one of those section 6 type problems. In order to compare e minus d to a number that happens to be 0, and again, don't let that confuse you. It's just easier than saying an elf is at least half a foot shorter than the dwarf. You'd have to think about that a little bit. So don't let the fact that this number is 0 confuse you. Well, we need rules for this. So we can use our normal procedures to compare this variable to the number 0 if we know three things. First of all, we've got to know that this thing is normally distributed. And then second of all, to get on with things, we need to know his mean and his standard deviation. Subtract, divide. So first of all, we're good to go. It is normally distributed because from what we said in section 6, when you add, or in this case, subtract two normal-shaped things, the result is another normal-shaped thing. So if E is normal-shaped and D is normal-shaped, then E minus D is normal-shaped. And then again, using our section 6 formulas, we knew how to find the mean and standard deviation. When you subtract two variables, you subtract their means. In the proper order, of course. There's no particular reason it should have to be positive. And if it's not, be careful when you're subtracting a negative. We're not flying entirely blind, right? It's the easiest thing in the world to lose a sign in these problems. But at the end of the day, considering what we know, elves tend to be taller than dwarves. At the end of you might happen to get a short elf, you might happen to get a tall dwarf, but on average, elves tend to be taller than dwarves. So at the end of the day, this should be on the unlikely side of things, right? The elf might happen to be shorter than the dwarf, but it's not the way to put your money. So if you do lose a sign or look at the wrong side of the chart, again, it's the easiest thing in the world to do. But when all said and done, a plausible answer is going to be less than a half, right? This is going to be on the unlikely side of things. How unlikely remains to be seen, but it's not going to be more than 0.5. So it's easy to make mistakes, but it's also easy to check those mistakes. Anyway, the mean of E minus D is the mean of E minus the mean of D in that order, 6 minus 4.8, which is positive 1.2. But as for standard deviations, remember, when you add or subtract variables from section 6, we know that you don't add or subtract the standard deviations. When you add or subtract variables, you don't add or subtract their standard deviations. You square them, add them, and take the square root. So remember, subtraction becomes addition, and also you got to square them, add them, and then take the square root. So three things going on there. First of all, it's not subtraction. Second of all, the formula is weird in any case. Square them, square root them. And third of all, remember, they had to be independent for those to work. What does that mean in this case? It means we're presuming that the elf we happen to pick has no bearing on the dwarf we happen to pick, and vice versa, right? So these are the rules when you go to pick the elf. Having picked the elf, these are still the rules when you go to pick the dwarf. The elf that you happen to pick has no bearing on what the dwarf is likely to be, and vice versa. The independence. And yeah, it's a safe thing to say in a case like this. You pick an elf, independently, you pick a dwarf. So we're good to go. Square them, add them, take the square root. And by the way, as long as I'm here, if we square 0.2 plus 0.5 squared, we're going to get 0.29. The square root of 0.29 is 0.5385 something. Now you only need enough accuracy to get z to two places. But the easiest thing to do on a calculator like mine anyway would be to type in 1.2, negative 1.2, 0 minus 1.2, right? Negative 1.2 divided by answer. And then I haven't lost any accuracy. Negative 2.283444058, that's more than I need to know. I only need z to two places, right, after the decimal. So negative 2.23 rounds up. Well, numerically speaking, it rounds up. So negative 2.23. We're comparing to the number that happens to be 0. We subtract the mean, and we divide by the standard deviation of the guy in question. We get negative 2.23, and it is unlikely in the extreme that 0.129. So it is unlikely in the extreme that the elf you pick is shorter than the dwarf you pick. And everything seems to track. At a guess, it's going to be unlikely. At a guess, it's going to be very unlikely. But, look at it this way. There's a 1%-ish, little more, There's about a 1% chance that the elf you pick is shorter than the dwarf. What is probability? 1% of the time that you pick, the elf will be shorter than the dwarf. So, it all depends on your perspective, but it's unlikely to happen next time. So nothing new there. It's a good old Section 6 type problem, just more of what we did in Section 6. Now let's take a straightforward Section 9 type problem, the new stuff that we've just got done talking about. And this is just going to be another example of what we've just got done doing. Take a simple random sample of 4 elves. What's the probability that their average height is less than 5.8 feet? So in other words, with the understanding that n is 4, we're talking about E bar, the average of 4 elves, being less than 5.8. Now, we didn't do that first type question that I alluded to. What's the probability that a particular elf is less than 5.8 feet? Logically, that should be unlikely, right? Logically, this should be even less likely, right? As unlikely it is that a random elf happens to be on the short side, it should be even less likely that the average of 4 is on the short side. So you can use a little common sense on this, but the bottom line is this is going to be less than a half, right? Because I don't have my bell picture ready to go, but at least I don't think I do. Nope. But, our bell picture here is, for the elves, is centered at 6. For a particular elf, it looks like this. Let's scroll up to a similar picture. So for a particular elf, it looks like the blue curve, centered at 6. For the average of 4 elves, it looks like the red curve, also centered at 6, but half as spread out. Square root of 4 as spread out. Anyway, taller and thinner. So if this is 6 and this is 5.8, then as unlikely as it is for a particular elf to be less than 5.8 feet, the blue area, it should be even less likely that the average of 4 should be that short, right? So let's check it out. In particular, it's going to be unlikely, right? If we're looking at the red here, then this is 6, and this is 5.8, and it's clearly less than half the area. So it's going to be on the unlikely side of things. Common sense, picture, however you want to parse it. Now remember that the rules for E bar, the average of 4 elves, it's still normal shaped because we're picking from something normal shaped in the first place, right? If elves are normal, then the average of 4 elves are still normal. This left-hand root. So the average of 4 elves is normal shaped. E bar is normal shaped with the same mean, 6, but the standard deviation, 0.2. This is how elves vary. How do the average of 4 elves vary? 0.2 divided by the square root of 4, right? 0.2 is the variation inherent in elves' heights. And then the average of 4 of them, 0.2 over the square root of 4. So the bottom line is, I should have something written down here like E bar is normal shaped, 6, 0.2 over the square root of 4. Say again, E bar is normal shaped, 6, 0.2 over the square root of 4. So there it is, right? If you want to compare E bar to this number, then from that number you're going to subtract 6, and you're going to divide by E bar's standard deviation, 0.2 over the square root of 4. 0.2 divided by 2, 0.1. Watch the order of operations. And in the end, that is -2, which we've done before, and recently it is 0.228. So it is unlikely in the extreme that the average of 4 elves' heights will be less than 5.8 feet. Now, what do I really want to get at? What I really want to do is problem 3. There was nothing particularly new about anything we just did. This was a section 6 type problem, comparing 2 variables. This was the kind of thing we've been doing in our straightforward section 9 stuff we've just got done talking about. looking at the average of a variable. Now what I want to do is put them together. What I want to do is talk about comparing one average to another average. In other words, I want to take the previous two problems and put them together. Take a simple random sample of two elves. Independently, I mean the elves we pick have no bearing on the dwarves we pick. Take a simple random sample of two dwarves. What is the probability that the average height of the elves will be less than the average height of the dwarves? Averages, section 9. Comparing variables, section 6. So you see we've got both things in play. On the outer level, it diagrams pretty much like problem 1, but with bars. So we're talking about E bar being less than D bar. We're talking about the average of two elves being less than the average of two dwarves. Now, by the way, notice that we've got two n's in play here. If you wanted to make it complicated, there's no reason it's got to be the same number of each, right? You've got the n for the elves, which is 2, and you've got the n, a different n for the dwarves, which is also happens to be 2. So if you want to compare E bar to D bar, then it's going to start out exactly the same way as it did above. E bar minus D bar is less than 0. And where do we arrive at? We're comparing E bar minus D bar, that creature, to this number, 0. Again, happens to be 0. Now, we hit it with a little bit of logic, right? Logically, before we can combine the means and standard deviations of E bar and D bar, we have to know them. So on the outer level, it plays out pretty much like the first problem, but on the inner level, it plays out like the second problem. So again, before you can talk about combining E bar and D bar and how their rules combine, you need rules for each, and that's the new part, right? So the section 9, make no mistake, this is probably the hardest problem type that we do in this neck of the course, but the new stuff is the easy part. Section 6, this type of problem here, is probably the hardest problem type we do, but if we build on it, we can make it harder. Nevertheless, it is the old stuff, it is the comparing variables stuff that is nasty. The new stuff, the highlighted stuff, is relatively easy. I say relatively easy because these are not nice numbers, and the reason I picked 2 of each instead of 4 or 100 or something that would be a perfect square is because that'll put me off the end of the chart. 2 of each is more than enough to make my point here, so I apologize for the numbers. So if you know how elves work, and they're normally distributed, then you know how the average of 2 elves work. And the bottom line is that the standard deviation gets divided by the square root of 2, right? If elves are normally distributed, then the average of 2 elves is normally distributed. And it's got the same mean as before, but as far as the standard deviation goes, well again, 2 things affect how the average of 2 elves vary. Number 1, the fact that we're talking about elves, and then secondly, the fact that we're talking about 2 of them, right? So the only twist on this is 0.2 over the square root of 2. Which, for what it's worth, if you want to do some intermediate rounding, which is never a good idea, 0.2 over the square root of 2 is 0.1414213 something. For verbal purposes, I'll call it 0.1414. In the end, we only need z to 2 places. I'm guessing 0.1414 is good enough to pull that off, but it's not a nice number. And then we do the same thing for the dwarves, right? So if we know the rules for the dwarves, they're normal, mean 4.8, standard deviation 0.5. Then the rules for the average of 2 dwarves, well, again, you just divide by the square root of how many you're averaging together. And for what it's worth, 0.5 divided by the square root of 2 is about 0.3536. 0.35355333906 call it 35, call it 0.3536. But better if you don't have to do any intermediate rounding. If you can do this all in one big gulp, then you don't have to worry about intermediate rounding. Wild guess, if you have each of these to 4 places, and then you go to combine them as we're going to see, it's probably enough to get you to the right z. But we do need z to 2 places, but beyond that, any additional accuracy is not going to change things. So then once you have this number instead of 0.2, and once you have this number instead of 0.5, then it plays out pretty much exactly the way that first one did on the outer level. It's a same type of problem. So in other words, exactly the way we combined the 0.2 and the 0.5, we're going to combine the new guys, right? E bar has this well, first of all, the means play out exactly as before, right? So the mean of E bar, the mean of D bar, if you want to know the mean of this guy, then it's going to be the mean of the one minus the mean of the other. So we're still going to subtract 1.2. Nothing new there. As for the standard deviations, it's exactly like what we did in the first problem, only the numbers are a little worse. So we'll take the standard deviation of E bar, and we'll take the standard deviation of D bar, and we'll square them, add them, take the square root. So in all of its unrounded glory, here it is, right? But if you prefer, it's approximately 0.1414 squared plus 0.3536 squared, and then square root it. And then negative 1.2 divided by that guy. So let me see how this plays out with a little rounding error. 0.1414 squared plus 3536 squared is 0.1450 something. And then if I do square root of answer, I get 0.3808. So this is in the general territory of 0.3808. And then if I do negative 1.2 divided by that, I'm going to get negative 315 and change, which rounds down. So negative 3.15. Negative 3.15 is way down here, right? I mean, it scarcely matters. They're not changing very much, but 0, 1, 2, 3, 4, 5. So it looks like it'll be this one. I mean, notice, by the way, that in this case, if you're one entry off, it's not really going to change things too much, so there's room to maneuver. But yeah, that's the 5 column. So negative 315, 0008. 8 times out of 10,000. Less than 1 time out of 1,000. Very, very unlikely. So it's very, very unlikely that the average of the 2 elves is shorter than the average of the 2 dwarves. Let's put a little perspective on this. Elves tend to be taller than dwarves. So in the first place, it should be unlikely that the elf that you happen to pick is shorter than the dwarf you happen to pick. But then logically, if you want the average of 2 elves less than the average of 2 dwarves, you're cutting even more against the grain, right? So not only should it be unlikely, but it should be even less likely than this. Logically, we're looking for a smaller answer than 1, right? And sure enough, that's what we're seeing. And that's the reason I do 2 of each. If I do 3 or 4 of each, I'm going to be off the end of the chart. And while that'll be pretty conclusive, it might be a little confusing as an example. What else? A visual aid here would be something like if you had a bell centered at 4.8 for the dwarves, and a bell centered at 6 for the elves, and there's going to be a little bit of overlap to those bells. So yeah, you could happen to get a tall dwarf, and you could happen to get a short elf, so they could cut against the grain. But if you divide these by the square root of 2, then you've got a taller, thinner bell centered at 4.8 for the dwarves, and a taller, thinner bell centered at 6 for the elves. And so there's even less overlap there, you see. And so for things to cut the wrong way, you've got to go even more against the grain, right? So logically, it should be even less likely. I think that's pretty much what I spell out in this paragraph here. Since elves average taller than dwarves, it's unlikely that a random elf will be shorter than a random dwarf. And the more of each you average together, the more unlikely it's going to be that the elves on average are shorter than the dwarves, right? So if you take 3 of each, it's going to be even less likely that the elves on average are shorter than the dwarves. 4 of each, even less likely. Probably you won't tell the difference because they're both going to be off the end of the chart. And again, this is what I was just saying a minute ago. As the averages become taller and thinner bells, around 6 and 4.8 respectively, it gets less and less likely that you're going to cut against the grain by happening to get a very big dwarf average and happening to get a very small elf average. The bigger the samples, the harder that's going to be to pull off. So yeah, anything is possible. You could get the 100 shortest elves in the world, and the 100 tallest dwarves in the world, but that would be extremely unlikely. It would be, cosmically unlikely. So it's not going to happen. I mean, anything might happen, but no, not that. So there's an example of how you can compare averages. There are some nice practice problems for these. Like I said, theoretically, those problems we did in Section 6 comparing averages are the worst type of problem we do in this middle part of the course. Call it the middle third. But if you build on it by comparing to averages, you can make it that much worse. On the other hand, it is the old Section 6 stuff that makes it worse, right? The new Section 9 stuff is comparatively simple. Put them together, of course, and it's worse than one of these, but it's the old stuff that's making it worse. There are some nice practice problems for some of these. Where are we? Section 9. So there's several of these type. So the basic Section 9 stuff is relatively straightforward and you can practice it. But if you want to talk about comparing averages, then you've got things like number 4. The average of 4 rolls of the pyramid, the average of 50 rolls of the pyramid, the average of 50 rolls of the cube. What's the probability that the one is at least something more than the other? That's a hard one because you're not comparing to 0 in this case. What else? Some of the more basic ones are number 9, the ice cream cones. The average ice cream weight from the one store is more than the average ice cream. The average of 5 cones from the one is greater than the average of 5 cones from the other store. That's a pretty straightforward example of what we were just talking about. Number 13, the average IQ of 3 students from the one university is more than the average IQ from the other university, or in this case, at least 5 points higher. So that's a little bit more complicated because it's got the 5 instead of the 0 going on. Let's see, there's no easy way I can fix this encoding thing, but this is just the curly parentheses and curly quotation marks that the encoding I have at the moment doesn't seem to like. Let's see, I thought I had one more of these in here someplace. I guess not. So comparing averages, we've got 4A, we've got 9, B and C, well, 9C, and 13C. And there's some more Section 6 stuff thrown in there as well, one of each. Notice, by the way, that the old Section 6 stuff kind of is incorporated by the Section 9 stuff, right? If you pick a sample of 1 each, that is, divide by the square root of 1, then that just takes you back to where we were in the first place, right? So, comparing averages, there's also one, I'm sure there's one on the Section 6 quiz, at least one on the Section 6 quiz. I think there's a couple of them, the Section 9 quiz. I believe there's 1 or 2 on the Section 6 quiz, and there's 1 or 2 on the Section 9 quiz, so you can get more practice at comparing variables. One of the harder things we do, not necessarily an omen of things to come, it's kind of a high water mark, comparing variables, and in particular comparing averages. This, by the way, concludes the middle part of the course, talking about the theory of statistics. And then starting in Section 10, things get, like I mentioned at least once before, the idea was to get the math out of the way in sections 7 through 9. So that if you take some time and absorb the section 8 and the basic section 9 type problems anyway, then what we're going to do next mathematically is going to be not that big a deal, because it's just variations on a theme. So much of what we do from here on in is just doing selected types of the problems we've already done. The section 8 stuff for p hat, the easier section 9 stuff for x bar, not so much the comparing we were just talking about. And the idea is that once you're really good at sections 8 and 9 in particular, then you're pretty much set on the math for the next few sections. What is going to be confusing, or shall we say the only new thing that is going to be confusing about sections 10 to 15 here, is going to be the logic of what we're doing. Real-world inference, making conclusions about the population from the sample you've already done, is philosophically weird, because again, it's the population that is what it is and can't be something else. There's nothing random about it. And the sample that you have just done used to be random and could have been something else. So thinking about probability backwards, that is to say, thinking about inference, is going to be philosophically weird. But if we've done our job with sections 8 and 9 in particular, then that's the only obstacle, is that it's going to be weird to think about properly, and the math and formulas, at least, should be comparatively old stuff, particularly by the time they become relevant round about section 11. So from here on in, I would say that the math gets considerably easier, or at least nothing particularly new. Whereas the ideas involved become a bit more complicated. When people stumble on the next several sections, 10 to 15, and they do, it's very hard to think about properly. But 9 times out of 10, when people stumble on this section 10 to 15 type stuff, it's not so much because of the math, at least if they're up to speed on the previous sections. It's because it's hard to think about properly. And let me just say that this will come with practice, because it is very redundant. There are not a lot of major ideas in play here. There's the idea of confidence intervals, there's the idea of hypothesis testing, and then there's the formulas for p hat and x bar that we've just got done talking about. And then everything that we do is just a variation on putting those 4 ideas together. So it will be very repetitive from here. Now let me just say, this can be a good thing or a bad thing. The one thing that confuses people about this latter part of the course we're about to embark upon, section 10 onward, practical statistics. How to use statistics in a practical way. The thing that confuses people about it is, I forgot where I was going with that sentence. Don't get old. It's the concepts involved. It's not the math so much. It's the idea of thinking about things in reverse. So I'm just struggling to recover my train of thought. But that was the gist, is that thinking about probability backwards is a little philosophically weird. Trying to conclude things about the population from the random sample that you just did is always going to be weird. But one thing you always want to bear in mind when you're making conclusions about the real world from the sample you just did, you always want to bear in mind that because of the randomness, you could be using a different sample. You could be using a different number for your statistic. So anything you conclude about a population from the statistic you happen to be using has to bear in mind that you could just as easily have a different sample and be using a different number for your statistic. Your results are only going to be as reliable as how likely was your sample to be something radically different. So at the end of the day, you can see the power of the standard deviation of a statistic. The standard deviation of a statistic tells you how likely you were to get a different result on a different sample. And if that's very high, then the sample you happen to have is not very reliable if you could just as easily have something very different, right? It's like the picture that we talked about with the targets, right? In the real world, the bullseye is invisible and you only get one shot. So, ignoring the bias issues, looking at these, if your statistic has a very high standard deviation, then you might have this shot, or you might have this shot, or you might have this shot. You might be close to the target, or you might not. Or to put it another way, the target might be close to the shot you happen to have, or it might not. But if you've got a standard deviation, if you've got a statistic with a very low standard deviation, then it really doesn't matter what shot you have, it's probably pretty close to the target. Turn it around, we're confident that the target is close to the one shot we did. So that's just enough to give you an indication of some of the problems we face trying to think about statistics backwards. There was something else in the back of my head, but I'm sure it'll come up again as we proceed, so no worries. So sections 1 to 6, background information, all the math and concepts you need so that the ideas in play will make sense. Sections 7 to 9, the theory of statistics, how it's supposed to work. In particular, the sampling distributions, the probability distributions, the patterns of randomness of a statistic, which are the key, as I said, to everything we do in the real world. If you want to know what you can conclude from the fact that you flipped if you want to know what you can conclude from the fact that you flipped a coin 100 times and got 65 heads, then the logical question to ask is, how likely are you to get close to half heads when you flip a coin 100 times? You see, you've got to have some context for 65% heads on 100 flips. 65% heads on 100 flips has got a totally different context from 65% heads on 30 flips or 1,000,000 flips. So this is all the power of the standard deviation of the statistic, and we'll see how all this comes together as we go on. Anyway, that is section 9 and a little bit extra, and we'll go on into the practical part of the course next time. My old videos from spring, I believe, start with about section 12, so I should only have about 2 more of these to do. And then in the latter part of the course, I can certainly do additional videos on an ad hoc basis, clearing up points, going over problems. I could do that now, I just haven't gotten any questions yet. And so I'm in the stretch as far as that goes. Just beware that things are going to get a bit anachronistic when we get to section 12. But the course doesn't really change too much from semester to semester, so I think I can get away with my old videos. And I can clear up any points that need to be cleared up with additional videos or discussion boards or any other things that haven't come up yet, having gotten very few questions, but we'll see how it goes. So section 10 next time.